My name is Mr. Monroe, and we're going to investigate and explore magnets. You know, the first time I saw a magnet, oh, a long time ago, I thought, wow, that is magic. I saw a magnet pull something to it, and I couldn't figure out what was going on. I thought the person that had the magnet was either very tricky or he had some magic about him. Then in science, I learned that there are certain things that have the ability to be attracted to one another. Now, that word attract means to pull, and magnets have that type of force. It is called a magnetic force, okay? And the part of the magnet that creates that force is called the magnetic field. Now, we know that there are very common magnets all around us. Probably ones that you would see in the classroom would be a bar magnet, which looks like this, and maybe a horseshoe magnet, looks like this, a U, or maybe even a ring magnet, which is just a circle with a hole in the middle like a donut. Now, they also come in different sizes. This to me is a large one. This is a medium, and this is a small horseshoe magnet. We also have a large bar magnet, and there are smaller bar magnets. And there are huge magnets that are being used in our world today, and they're used in our everyday lives. In fact, there's another type of magnet that I've seen working, and it's called an electromagnet. And it's really strong because it's also using an electrical current. But you know, students, listen, magnets are found in our everyday lives, and I've showed you these common magnets. They have a strong pull to objects that are made up of maybe a little bit of iron or a little bit of steel. And when that happens, the strongest part of a magnet has that pull toward those objects. We call those the poles of the magnet. For example, with this horseshoe, if we look real close, and I don't know whether you can see it, there's an S and there's an N. That S stands for the South Pole. The N stands for the North Pole. And that's where the strongest pull, the strongest magnetic force is located in a magnet. With the bar magnet, S stands for South Pole, N stands for North Pole. The strongest magnetic field, the strongest attraction points are those points. And then with the ring magnet, one side would be considered the North Pole, the other side would be the South Pole. Now, students, magnets, again, are attracted to objects that have a makeup in them of either iron or steel. We're going to run a test on some objects that I'm going to put together. I've got a bunch of stuff in this Petri dish. And I'm going to select some of these items, some of these objects to put in a dish, and we're going to test them. We're going to put a rock, a nail, a big brad. Now, I don't know whether that's going to be attracted to a magnet or not because it's gold in color. Let's see. Pop top from a soda can. Got some interesting things. A screw. Paper clip. A bead that came from this necklace, a silver, I guess it's silver. I don't know what it's made of, but we'll find out in a minute. And let's put a little money in here, okay? How about a penny? I believe that's enough stuff. Well, let's try this. This is a funny shaped paper clip, so let's put that in there. And how about a thumbtack? Okay, now I'm going to use a small bar magnet to test these items to see which ones are going to be pulled up by the bar magnet. Wow, it's pulling some stuff up. Let's see. Can it get it all? Let's see. We're working on it. Oh, it's trying to get everything. Let's see here. I believe it got all it's going to get. I see the thumbtack is on there. I see the brad is on there. I see the bead is on there. I see the nail, the paper clip, and the screw. So all of those objects must have a little steel, a little iron in their makeup. It did drop that tack. Let's see if we picked it right back up. So all of those items were attracted to the magnet. Now again, attraction or attracted means it pulled it to it. Okay, now I'm going to get rid of that. And I'll show you what was left. The rock, didn't pull that up. The aluminum pop top from a soda can, it didn't pull that up simply because it's made out of a metal called aluminum. The penny, it did not pull that up because a penny is made out of copper. And of course, this weird paper clip, it's made out of plastic. So the items that were left behind, they didn't have any iron or steel in their makeup, okay? Now, as far as a pushing force, in magnets, we call that repelling or pushing away. And magnets have that tendency to do that to each other. Take, for example, these two small bar magnets. Now, you heard me talk about the north pole of a magnet. If I take the north pole of this bar magnet and the north pole of this bar magnet, and I try to put them together, they're not attracted to each other. In fact, they are repelling against each other. They're pushing away. So that, in a sense, is the ability to push with magnets when you have two magnets with like poles facing each other. Now, if I reverse this and put the south pole next to the north pole, look what happens. They attract each other. Another good example would be this ring magnet. There are two rings already on the shaft of this little stand. If I put this ring magnet on there, it doesn't go all the way down, does it? It bounces up and down because, you know what? I know that gravity's pulling it down. You heard Ms. Fuller talk about gravity, but there's enough magnetic force going on between these two ring magnets, probably like poles, like I said. Probably this is the North Pole, or maybe that's the North Pole. They are repelling. They are pushing against each other, not letting this come down. It could be the South Pole, or that could be the South Pole, but they are like poles. Now, students, listen. I used to be really curious when I was young. And I was trying to figure out that magnet. At first, I thought it was magic, but then I realized it had something to do with science. So I got to wondering who might have discovered the magnet, and tried to find out back then and couldn't find out a person or famous scientist that had discovered the magnet. I saw a lot of stories that had been made up about how the magnet had been discovered in the natural world, meaning out in nature. And you know, I wish I had time, I could tell you a little story about that, but I don't have the time. But evidently, it was discovered in a mountain. And this mountain had rocks that were like magnets. And the name of that rock formation, the different rock formation, is called magnetite. And it looks like rock formations like this tiny rock that is magnetite. Another name for it, it is called lodestone. So it's a natural magnet. Now, there are places you can find these rock formations all over the world, but in large quantities, the closest rock formation that we know of that has a lot of magnetite would be in the states of Arkansas and Louisiana. So it is a natural magnet. As I can show you, it will be attracted to items that are made out of steel or out of iron, okay? Now, magnets are used in our everyday lives. They're used in electric motors. They're used in generators that make electricity. And I'm thinking of something else that they're used in too. You know, maybe you've been on a trip with your family, maybe gone camping, hiking. I know that a lot of times when people go hiking and camping, they carry a little tool to keep them from getting lost. It is called a compass. And what people don't realize is that, I guess they do realize it, they know how it works. But inside that compass, there's a needle, and that needle tells you which way north is, because north is on a compass, it's the N. It tells you what direction east is with an E, and south and west. S for south and W for west. Well, that compass works simply because it is said that our planet Earth is like a big compass. And it's like a big compass because at the top part of our planet, we call that the North Pole. At the bottom part of our planet, we call it the South Pole. And I can remember, well, just like coming up now, I know some of you are thinking about Christmas. Well, way back when I was a little fella, I just knew that Santa Claus was coming in from the North Pole. And he may be on his way. It may take him a while. But listen, people refer, or scientists refer to the North Pole as being the magnetic north. So that means that's how a compass works. That needle that's inside of a compass will point toward the direction of north, simply because of being pulled or attracted to the north. Now, I know that north in my classroom is that direction, okay? So this compass right now, I don't know whether you can see the needle, but it is pointing that direction. So I know that's north. What I'm going to do, I've made a homemade compass here. And I want to show you guys what I did. I took a magnet and I suspended it on a stick. And right now it's kind of working, it's flopping back and forth, but eventually it's spinning back that direction. It's trying to work its way to find the north. And eventually it's going to settle and it's going to show you which way north is. It's going to work back and forth. Here it goes. Yeah, it's working. It's trying to get there, isn't it? And I don't have much time, so when it gets close, I'm going to stop you. But we do know it's trying to work its way back to this direction. And it's slowly getting there. But you know, there's one thing that will mess a compass up. And if you are out there and you're using a compass and you walk up on a rock formation of lodestone or magnetite, guess what's going to happen to that compass? It's going to go crazy. It's going to start spinning. That needle is going to start spinning because it's attracted to magnetite, even going the other way. Look at that. So without any other magnets around, a compass will work. And students, hopefully today, you've learned a little bit more about magnets and how they can pull, attract, and how they can repel.